it's really weird to be out speaking at conferences again, or meetups, or whatever you want to call them. But it's really nice to have an audience instead of just speaking to a camera. So I'm really enjoying this, at least so far. We'll see how I feel about it in an hour. Let's see if we can get this to work. Oh, here we are. I think we're on. So the title of the presentation here is about ESP32s. It's a kind of microcontroller, so if you don't know the ESP32, just think microcontroller or very cheap computer. It's also about serviceability, which is a term that some people know. Others just think it sounds really good, and this is the reason why I put it on the first slide. It sounds like something you want to have. I guess we have to try to figure out what it really is. But the combination is a very powerful one, so that's what I'm trying to sort of argue for here, is something that you want serviceability and you need ESP32s, or microcontrollers in general. So I'm Kasper. I have a sort of a dark past at Google where I spent a decade building probably your browser. At least the V8 JavaScript engine in there has had sort of good success and ended up in Chrome and in Microsoft's Edge browser as well. So it's fairly widely used, and through that work, we managed to screw up the internet a number of times. I broke Gmail in Egypt at some point, made it impossible to log into Facebook. Apparently, that was worse than Gmail in Egypt. But I think through the work, we also made JavaScript and the web a lot faster. And with my good colleague and friend Lars, we actually started Toit based on sort of that success on the web, and thought, hey, if we can do something great for the web, maybe there are other areas where what we know can be applied, and that's a starting point for Toit. Lars and I were not the only ones. Sort of found a good team of people from Google, and primarily Google and Uber here in Aarhus, and started the company based on those. And together we've built software for, it's kind of weird to say, but for billions of devices. And quite honestly, the only place we could find where there might be more devices than that was in the sort of the embedded or the IoT space. So that's why we went for that. Like, how do you top 3 billion installs of Chrome? You go for IoT and try to find a way to make a difference on small devices. At least that's sort of what we thought. We're also sitting here in Aarhus, just sort of on the harbor here. So it's a local startup here in Aarhus, Denmark, where we're really trying to build the next generation software platform for IoT. In 2018, when we were just sort of starting to embark on this journey, we learned of this chip, this setup, the ESP32, and we thought this is neat. You can get a very powerful little dual-core 240 megahertz RISC CPU, coupled with enough RAM to do interesting things, flash, built-in Wi-Fi, built-in connectivity options for you, for less than $2 when you buy a lot of them, and actually when you only buy a few, it's still sort of in that category. Even the development kits are really cheap, so you can buy them and pass them around and give them away basically for almost free. And we thought, this is almost too good to be true. I mean, this is a more powerful computer than the ones we had when we started building Java systems for servers back in the day, right? So it's kind of weird that you can get this for this price, but we thought, okay, we'll take that. Maybe the most important thing is really sort of what's in the middle here. Like, it runs well on batteries. So you can get these general purpose CPUs that have power save modes built in, where they can go to sleep and consume pretty much no power. So in practical settings, we see around 10 microamps, which is very low. And that means that you can run on completely standard industrial batteries, like AA batteries you can buy in IKEA, for a couple of years, and do meaningful things every single day based on that. That's quite attractive. And we actually think that for a lot of the cases where this fits, what it's up against is really more complicated, more sort of heavy hit setups like the Raspberry Pi setups of the world. So we actually find that there are lots of cases where sort of a small, very cheap system that runs well on batteries can sort of go head to head with Raspberry Pis. And maybe the battery thing here is really, in addition to the price, it's really the significant part, because it's really, really nice to be able to run on batteries, and that's just hard to do with Raspberry Pi. Unlike unless you take like an automotive battery and put it next to it, which seems like overkill for most setups. So we actually find that there's just like a lot of sort of simple cases where like the compute power of a Raspberry Pi is way overkill for what you're trying to do, like read some measurements from peripherals and control some operations from that. So that made us think there are lots of people that are excited about Raspberry Pis, lots of people that find it hard to do things with that. Maybe that's an interesting space to work in. So we went for that, and we were encouraged by the fact that ESP32 is all over the place. It's used in so many applications that you've never heard about. But if you want to find get a glimpse of what it might be used for, go to AliExpress or Banggood or some of the Asian vendors here and just search for it, and you'll find the weirdest kind of robots and things based on the ESP32. And if you actually look deeper, you'll find lots and lots of consumer products, probably in your houses, that have ESP32s in them. In this embedded space, you never quite know because they are embedded and hidden. But dishwashers and washing machines from some of the major brands are using these chips today. So it's very much not just a toy thing, it's an industrial choice as well. And it's really growing phenomenally. If you look for this as a place to run your code on, the place you would start is actually using Esp32, the company behind the ESP32's development framework. And it's all open source on GitHub, and you can go there and you can download and work with this thing. And you can get very far with that. So they actually built a reasonably nice software development kit for these devices. But I think if you come to this from a Raspberry Pi background and you expect to be able to run high-level code, Python, and be flexible and do continuous integration delivery, you'll miss some things. There are things that are just hard to do on microcontrollers, even with a healthy layer, a healthy operating system, if you will, a development kit here underneath. They're just challenging to bridge the gap between what software people can do well and what the firmware, hardware folks of the world demand of you if you enter this space. And I think there are a couple of reasons why it kind of sucks to do this. I mean, it can be fun, but it's also hard to do this at the right quality. And reason number one is that the separation between your code and the system, like the drivers, the operating system, everything that fits in there, is almost non-existent. That means that if you screw up, you will mess up the entire system, everything will fail together, and you're not going to be in for a nice ride. So that kind of operational safety that you get from running on a real operating system like Linux or Mac OS, or on some of the phone OSs, it's not there. Like what you run on is much more primitive. Usually, all the software on these devices is compiled and linked together and shipped together, so it's very sort of closely knit, and it's tend to be fairly specifically tied to hardware from a very sort of early state. So it's rarely separated nicely, and it's very uncommon that you have lots of code sharing across different kinds of devices here. So you feel like you're sort of writing a different kind of software, and people also tend to call it firmware instead. The kind of languages that are in front of you, if you go here, are some of my favorite languages, but it's not really everyone's favorite languages. Low-level languages, manual memory management, C, assembly. I kind of like assembly more than C. I'm not quite sure why. It feels like it makes me all powerful, and I kind of like that. In practice, it doesn't make me super productive, but I still like it. Maybe the hardest thing is to just realize that it's all on you, right? If you make a mistake, you often crash the entire device, and sometimes crashing is the good case, because one thing is crashing a device and it reboots and you can start over, but actually bricking it, making it impossible to get it back online is much worse. So if you end up doing that, you need to find a much more sort of a heavy approach to getting it back online, potentially actually wiring it up and using a serial cable, and it feels like if you're always worried about doing these things and getting them wrong, you're probably not being super innovative and pushing things, you're not experimenting, because the cost of getting it wrong is very high. And I think as you're looking at this, you're looking at C compilers and USB serial flashing, and it takes a long time. I mean, you can't push a change and within a few seconds see the result of that. And I think once you're used to that way of working with a healthy software system, it's very hard to go back. It's just very challenging to go back to a model where it takes you a few minutes to see anything, at least if you've tried something else. So I think, in some sense, the way of saying it is just like the way you develop functionality for these devices doesn't compare favorably with the way you develop software for a desktop system or a mobile phone. Like the experience is just very different, and it feels a bit dated. It feels like you're sort of back in the sort of the soldering iron camps, and you have very low-level tools, and you see a lot of sort of conservatism in that industry coming from that. Like the tools are well-known, established and old, and very high quality often, but it doesn't really make it possible for you guys to build something and ship it tomorrow and trust that the quality is right. It takes much, much longer. And the reason really is that it's all firmware. And people talk about firmware as this fantastic thing, and in some sense it is. It is often sort of the foundational thing that you put on your devices. And it is firm. It does mean that it's hard to change, right? Just like concrete. If you kind of build it and it's a good foundation. If you get it wrong though, I mean, if you do it the wrong way, like you have entire buildings that need to be like torn down and rebuilt. Like it's a very hard thing to work in that space when you cannot change your mind later. And I'm not suggesting that we should build the next building down here on top of Lego, but in terms of being soft and manageable and changeable, I think that's much closer to what we like to use as software developers. Like tools that are composable, we can change our minds, we can try things, and we can learn fast. Did I say something? It's voice activated, I guess. I mentioned Lego. Maybe that's the keyword. Anyway, I think so. The sort of the analogy here is kind of broken. That you probably wouldn't want to build a house out of Legos, even though I know people have tried. But the fact that you can build things, you can test, you can try, you can learn really quickly. I mean, it is very, very attractive. I think for all the software folks here. And I think there's just a number of things you can do because of software versus firmware. Just in terms of speeding things up, moving faster, and getting ultimately to higher quality products. I know a guy who said that friends don't let friends waste their time on firmware. He was clearly a software guy, but I think there's some truth to that. There are just so many things you couldn't do if all you interacted with was firmware. I think we need software around us to get productive. And I think I have evidence for this, right? I have movies where you end up not being eaten by dinosaurs because you're interacting with software systems. Like, if this girl was interacting with firmware, it would not really have helped that she knew the system already because it would be locked and set. She couldn't change anything, do anything to it, right? So I think that the notion of flexible, adaptable, changeable, reconfigurable systems is so close to us and so important to us that it feels weird to go into a space where that's not the case. So I don't know if you know the reference, but otherwise you can look it up. It's a Unix system. So the reason why she could fix the whole thing here and save the world or the dinosaurs or whatever it was that she actually had a serviceable platform, a Unix system that she could interact with. She could do things to. She could install, configure, fix bugs, monitor, understand, and actually she could sort of restore system functionality that was broken down. And I think that's the key about serviceability here compared to something like observability that has gotten a lot of attention lately. Observing is just, it's super important. You learn, you see what's happening out there, but being able to service something requires that next level of control, that you can do things to it, reconfigure, change, adapt, move forward. So I think serviceability is, it's a classical word in this context, but I think it's been forgotten a little bit. I think we all sort of expect things to be serviceable, from our iPhones to our computer systems. They should be serviceable, repairable, upgradable. But in practice, I think we do surround ourselves with lots of things, in particular on the hardware side, that is not particularly serviceable. And I think what we find from that is that things get dated, broken, kind of lose their value over time to a much higher extent than any kind of software system. There's a saying that software is eating the world, and I think what we'll find over the next decade is that will apply also to these spaces of microcontroller-driven designs and hardware systems. And I think the reason why it will eat the world here is actually because of things like serviceability. It's just a much, much faster, much more healthy way of doing functionality. And I know you all know examples where people get this wrong and they use the serviceability to like break the system after a while, and like that update you got to your app on the iPhone was really annoying because it made things worse. So it's not, it's a double-edged sword. There's something nice about locking down things that actually work, but I think overall for an industry, locking things down too early is a big problem for us. So serviceability, I think it's really key here. So the big question is really like, how do you get serviceability for a microcontroller, for an ESP32? What does it require that microcontroller to do? What does it need to be able to achieve to actually be what I would consider serviceable? I think the most important one, and one that's easy to forget, is really the sort of keep on trucking part. It has to keep running. I think if it gets brick or doesn't go online, you can't really service it. If it gets stuck, there's nothing you can do. So it needs to be robust and resilient to the kind of issues that I tend to introduce, or you guys tend to introduce in code. It has to be able to deal with that well. So you need some foundational layer that gives you those guarantees that make it possible for the system to assure you that it's going to keep on trucking. It also needs that observability part, right? It needs to be able to tell you what actually is happening on the device. And it needs to be able to do that even when it's sort of out in the world. So that remote observability for devices is really, really important. And I think we see lots of sort of exciting things happening in that space, from people building observability stacks for devices to companies like Humio that does the log processing for all those events, so you can get insights from a vast population of devices and things out there. So like the event logging and metrics gathering and getting insights from that is really key to building systems that over time perform well and over time give you those insights that you can continue to push and tweak the behavior. I think the last part here about asking for direction is more of a sort of a tactical thing. We found that in order for something to be serviceable over time, the easiest way of achieving that is to actually instrument it to be good at asking for direction from the outside. Instead of having too many fixed patterns or algorithms built in for how it does things, if you can find a way of making it sort of scriptable from the outside, giving another system that is easier to upgrade, possibly a cloud-based one, the ability to sort of tell it what to do in some meaningful steps, that is basically implement mechanisms that will allow you to upgrade service, deal with that outside, and worry less about policy there. So in some sense, it's a way of dumbing down the device in terms of how you service it and saying it only needs to implement some protocol that allows you to do these things. What you want to do with it needs to be scripted from the outside, because that's the challenging part, and that's the thing you want to be able to update and change your minds on really quickly. So think of it as a small scripting engine on the side that just tells us the external orchestrator, I'm here and I'm ready to upgrade, install, do things for you, just tell me what to do. So that, I think with those three things, you have the foundation for building serviceability even on small devices. And it's all very achievable on a microcontroller that costs less than $2. Keep on trucking, that requires some work to make it robust. Tell what's going on. You need to gather information from the device and package it up and send it somewhere where it's meaningful. And ask for direction is mostly the protocol that you use to communicate with the server side of things that needs to be constructed in a way where the device doesn't make too many decisions on its own, because if they're wrong, you have a critical bug in that part of the system that's supposed to help you get rid of that next level of bugs, which is a challenge. One good thing is that at least I've got a hammer, and I think some of my colleagues have a hammer as well, and that hammer is really a virtual machine. And this is, I know there's a saying that if you have a hammer, everything looks like a nail. I think it's exactly right. So in some sense, I always come at these problems and say, oh, maybe that needs a new language, a virtual machine, and some compilers. But it really is true in this case that we found that like a virtual machine, a software abstraction that you can put on these devices that heighten the abstraction level of the device and give it those three qualities is a very meaningful way of thinking of it. And a virtual machine in this context is something quite close to the hardware here, and we sort of tried to illustrate that. So you can think of it as sitting on the device, putting sort of a shield between the hardware and the applications that run on top. And I'll dive a little bit more into how that works in practice, but think of it as the kind of operating system these devices should have had, and I think I'll be perfectly okay if you think of this as an operating system rather than a virtual machine. It's just, having worked on Java and JavaScript and Dart and other things, we always just call these things virtual machines, and they're just very close to sort of operating systems and systems that support running things on the device. But with that kind of thing in there, and with an API on the side, a serviceability API that is hosted in the cloud, you actually do have a system that allows you to change what's running on the device. The virtual machine becomes that implementation of that serviceability API on the device. There is some kind of protocol hiding behind that plus, but in practice, you just sort of get an API for your devices that allows you to service it, and we make sure that the device can keep on trucking if you put the division by 0 on the device, it's not going to fail dramatically. It's going to tell you something went wrong, and it's just going to be a pleasant experience. It feels like this should be table stakes. Like, this is sort of what you would expect from pretty much any other development environment, that if you get it wrong, you'll be told, and the world will not go down. But in this context, it is kind of novel. We're not the only ones suggesting doing a VM on devices. There are lots of others that are in that space. We're just really, really good at building those things. So we think that we have a leg up there in terms of performance and robustness, because that's not what we've been doing for the last couple of decades. It feels really weird to say that we've been doing anything for like decades, but it's true. So a virtual machine gives us the ability to do what we think of as cloud-managed containers on microcontrollers. Containers might be a bit of a stretch in the sense that it's a word often used in a specific cloud context, and we really think of device software running in small, isolated sandboxes on these devices instead. But if you think of it as a sort of an abstraction, it is really small containers, isolated units that run on these devices. And this is a stark contrast to like the kind of systems that you usually have on these devices, where everything is compiled together and there is essentially no containers at all. Everything has access to the same memory, everything runs together on these devices. So we give you like a sandbox environment for this ESP32 that can be fully controlled through a rich cloud API. I think one way of thinking of it is, how many of you are familiar with like modern cloud environments, like Google Cloud, Amazon Web Services? I mean, it's fairly sort of spread out these days, so lots of people here are familiar with that. That offers like a platform as a service abstraction to you. So you can engage with the APIs there and build functionality and run functionality on Amazon's or Google servers. In some sense, we're building exactly the same thing, instead the only difference is that we don't have the luxury of running all the code in one data center. It really needs to be out in the real world, on walls and fridges and everywhere to make sense. But I think if you can sort of get past that distinction, it really is like a platform as a service where the code runs partly in the cloud and partly on the devices. I think if you have a computer science background, you might think of this as a distributed operating system that covers cloud and the devices. Others think of it like a hybrid cloud edge thingy. I think there are just like too many names and too many different ways of describing it. So we went for this, okay, it's really small containers on microcontrollers. And the way it looks is something like this, right? The traditional is one I talked about before. You have devices at the core, hardware. You put this operating system, in this case it's the IoT development framework from Esp32, IDF. And then you put everything on top of that with no isolation. And it's sort of all firmware, compiled, linked, and dealt with together. On the Toit side of things, at the bottom of this, it looks the same, but just above that primitive real-time operating system, in this case FreeRTOS from Amazon, we put a virtual machine. And once we have that in there, things start looking more like Unix processes and systems that you might know from other places. Individually compiled and developed and deployed applications that run side by side in their own containers, and together they form the functionality of this device. And the nice thing is that we actually see users and customers gravitate towards decomposing their functionality into smaller units, and they do this because there might be different levels of criticality involved too, right? Some of it you might be very comfortable pushing changes to very, very frequently, like the UI parts might be something where you want to experiment quickly, whereas the core connectivity or data gathering part might be something where you're just a little bit more hesitant. And there it's really nice that you can split it up and have a different kind of deployment, testing schedule for these things. So I think with this, the firmware gets much smaller, and sort of from the virtual machine and up, it's all software. And it's all serviceable software. Does it make sense? And once you have a serviceable platform in front of you, you can start thinking of this exactly like Google and others want to think of this. It's a system that you can engage with and interact with. And the first thing you want to build with that is really like a dashboard, a place to go get insights and see what the system is doing. So we provide a console for your device fleet, a way to get insights into how that fleet of devices is doing. Much like your Kubernetes services are running in the cloud, you can go see, are they still there, what are they doing, how they connected, all those things, right? And it's really about gaining insights and monitoring. And I think to some extent it's also about changing and experimenting. But there is a limit on how many changes you want to do in a UI. I think most developers end up wanting to do something that's more code-driven, something that's scripted, something that's done through an API instead, just to have a healthy track record of who did what when. So we actually find that people mostly use like the dashboard, the console, as a way to learn, understand, and try a few things out. But in terms of deploying and dealing with class of devices, people tend to script it from the outside instead. So there's a command line tooling as well, which is probably more what you would use for a sort of high scale. I think the important part here really is the console, like the dashboard, is just one way of using that API for devices. And like the API is an open API based on gRPC. I guess my Google background shines through here. So we picked a sort of a declarative language for describing the service, which is something that you can access from any kind of environment or language. And it allows you to have this sort of rich API for doing things, servicing your device fleet. That really includes configuration changes, which is like a big source of errors in reality. Most people think that like code changes are to blame for most of the problems you experience online. In practice, at least we found at Google that the most sort of innocent configuration changes were often the ones that were the hardest to catch and the ones that had the most widespread issues associated with them. So clearly you need to be able to update configurations and deal with that. Installing, updating, removing applications is also important. And also, most of the IoT cases we have today are heavily centered around data, getting data from the devices. We've built a sort of a publish-subscribe mechanism that makes it really easy. If you're familiar with MQTT and systems like that, you'll feel right at home. But the idea is really that we need to make it very simple to publish data, structured data from the device, get it to the cloud, and vice versa. If you want to push data to it, it needs to be the same kind of system. And the only thing that's a little bit challenging here in this context, well, maybe it's not the only thing, but what's different here is really that most of these devices, they do tend to go to sleep quite often. To save power, they go to sleep. They stop being connected for longer periods of time. So what you need to build here is something that is inherently capable of dealing with that sort of async behavior in there. So we found that the best way of doing that is instead of telling devices what they need to do right now, instead of sort of instructing them and guiding them in the steps that they have to go through, it's much better to tell a system what kind of goal state you want these devices to achieve. Like instead of saying upgrade device A to firmware X, you say I really want device A to end up in a state where it runs firmware X. And then we have sort of an orchestration engine that deals with that and tries to be smart about how to schedule these changes. And that goes to the data side as well. If the device is not connected while it's gathering data, you need to be able to store it locally for a while before you bundle it up and send it to the cloud. So that sort of whole model needs to be built in and dealt with in a nice way. And it even needs to deal with the case that you gather so much data that from a certain point you sort of need to force the connection to happen because you got something very valuable that you want to offload right now. So the classical, this device has a fixed interval where it always connects every 3 hours, is usually not good enough for most cases here when you get a little bit more complexity at the edge on these devices. So the rich API allows us to achieve this, right? You take source code, and it's really hard to find a good picture of source code. I think this is actually a pretty awesome attempt. It says thumbs up, so I guess it's good. I really don't like how source code and those things are usually portrayed in movies, but this could be the odd case out. I probably need to see it at some point. But at least you take source code and you push it through the gRPC API. So in some sense, there is a part of the API that has an area where you can put in text strings, and that is really where you throw your source code in, and then it goes through all these hoops over Wi-Fi on narrowband IoT, and then it ends up in a form that's runnable on those devices without you doing anything else, right? So in some sense, you get this abstraction that you have a system where you can just give it code and it will run it on devices over some connectivity. And it works well over Wi-Fi, and it works well over modern cellular connections. You need a little bit of bandwidth to push these applications, but they're typically in some orders of kilobytes, not megabytes. So you can do really well on those low bandwidth connections too, like narrowband IoT. Like LoRa, Sigfox might be a challenge, and we typically don't see people updating firmware or applications very often over those, even though there are some that are trying to do that because it's kind of like testing the limits on how much you can pass there. Like if you're not familiar with LoRa or Sigfox, they're just like extremely low bandwidth, low power ways of communicating. So it's more like sending like 14 characters of information than it's sending an image of a Hollywood movie over. It's kind of impossible over those things. So I think if you only remember one thing from this, right, it's like this guy Jake, or this source code can fly over gRPC and end up on your devices over Wi-Fi and never NRT. And it's a great way of getting code, your code, running on devices without you having to worry about all the things happening in between and without worrying about what happens when it crashes on the device. We take care of that for you. And because we wanted to get all the properties that a VM allows you, we really needed to look at like what kind of language can you run on these things. So that text string, your source code that you send to us, we need to come up with a format for that. And in some sense, a format for text strings, it's sort of a language. So we thought maybe we have another excuse to do language work in this context, build something that we feel like is a really good attempt at building a high-level, approachable, understandable language for IoT. So of course we did that. We built the Toit language to enable this kind of high-level programming for these devices. And I don't know how many of you are familiar with how you do languages. A lot of it is gut feel, working with users and adapting, changing. So we've seen the language over some years now change and sort of get some flavor to it based on how we've seen people use it. But there's also a lot of sort of taste involved. And I'm sure some of you will find this quite pleasing and others will find that that is rubbing you the wrong way. But that shouldn't hold me back. I'll show you how it looks like. So here's probably the simplest or most canonical example of a programming language. It's the hello world. You can see that it's an indentation-based language like Python. Has way fewer parentheses than Python though. So the way you define a method, main, is by writing main, colon, indenting, and then the body of the message go there. There's something really nice about not having to do the end brace part. Clearly, indentation, significant white space is a hot topic for some. It's like, I don't really like it. I want to be able to format however I want to, shouldn't change anything. However, I think what we found over time is that like the logical conclusion of that is that the indentation doesn't really matter, and it does. I think for anyone writing or reading code, it does matter. You find bugs in code because people were misguided by the indentation. So there's something at least to be said for this. The reason why I kind of like it here is that it feels enormously light. There's just less clutter, and there's no sort of long sequences of end braces that you have to worry about, like in Lisp where there are like 9 end parentheses in a row for you to complete something. There's something nice about not having to do that. Just indenting 4 levels out doesn't require 4 new characters. It requires less characters actually. So that's hello world. Defining a local variable, message, and printing it. Super simple. Print is a method call here, not something built in, and you'll see a few more examples like this. More functions. Turn the square of x. So you can easily imagine how this sort of generalizes to more interesting functions. Clearly, you can also you might want to express types in your system. I think the Python folks are also coming around to that to some extent. We thought that we wanted to have a light syntax for that. So we went to something that probably feels a little bit foreign, the slash for the type, but I think it grows on you, and we found that writing the return type at the end is actually a healthy choice here because it's rarely the thing that you want to see first. So this is the type annotated version of a method that returns this, in this case, the sum of the sum of the double of the given x. Yeah. The way you would define classes interface is very sort of classical here. Less ceremony than in Python, where some of these things are not really built in. There are lots of like underscore init methods and things going on in Python, so we just sort of simplified that. But other than that, you can see that we sort of took a clue from Python here in terms of how we wrote the syntax. Here we have a main method defining a car, calling a method car.drive, passing a parameter 70 to that. There are interfaces, and it's a general purpose object-oriented language. So it's more the context of it that's novel than the language itself, but it sort of tends to get out of the way really quickly and make it possible for you guys to build sort of high-level code on these devices very early on. One area we did do a lot of work on was in the area of allowing you to express user-defined control structures. So one of the things that's really nice about sort of modern languages is that function expressions and lambdas and all these things have gotten a sort of a renaissance. They're getting popular, and they're used to structure code, and they're used to structure the way you use APIs and you think of things. So here there's a definition of a method called when that takes a condition, probably supposed to be a Boolean, and it takes a body that's actually a block. So there's a special type here for these blocks. And it says that if the condition is true, we'll call the block. And the way you can then use it is just like any other built-in control flow structures. You just call it and use the colons. There are no extra parentheses, just sort of fits in. This looks exactly like an if or a while. It's the same kind of thing. So in some cases, we sort of just implemented an if here in the language, which seems like a silly thing to do. But imagine this was a way to do structured logging. I want to log before and after doing these things. I want to structure my things. I want to have synchronization, all these things, and then be built in libraries rather than in the core language, which is tremendous help as you as you're sort of evolving a system, because you get much more flexibility through that. The blocks are actually stack allocated, so it doesn't require memory allocation on the heap to do these things, which is a big plus in terms of these small devices. So in some ways, we're just doing what is from Pascal known as local functions, and you just have a way of saying we're going to pass a local defined thing. You cannot stall that somewhere weird and call it later, but as this call is still active, here is a way of calling code provided by the caller instead. Probably all sounds super complicated, but it's really, really useful, especially because it's implemented so efficiently. One of the things that I find personally most sort of annoying with the whole sort of async Node.js world is really around waiting and dealing with things that come later. And there's like a whole promise and async await approach to this, but at some level at least, we're just working around the fact that it used to be extremely expensive to do another operating system level thread. So we're trying to get more value out of a single thread by getting it to do more things and writing code in a form that allows it to not block, but instead keep on doing the next thing. So we have this sort of interleaved spaghetti monster of an event loop on these threads that then end up calling and servicing lots of different parts. And they all have these sort of cutoff points where they cannot continue. So instead of stopping there, they actually find a way of returning and then picking up later, which is sort of an elegant model in some sense, and it's quite performant, but it really tries to work around the fact that threads are expensive. So what if you had really, really cheap threads? In this case, we call them tasks, where it's okay to fire off 500 of them, even on a small device. What would happen then? Could you write code in a different way? And here's an example of what you could do with this. I'm not suggesting that this is a great way of sorting a list, but if you go ahead and look at this, right? We generate a list, 10 elements with random values, print it out first, and it gets over here, you can see here the list, not sorted. And then we say, run through the list, and for every single element in this list, create a new task. Get it to sleep for a number of milliseconds that correspond to the value that you just found. So in this case, it would sleep for 224 milliseconds, and then print it out. And then when you run this, the entry that causes the least amount of sleeping will be printed first. So then you just need to grab the output from standard out, and you have your sorted list. It's probably not the best approach to sorting. It might be the only approach to sorting you hear about today. I would not recommend doing this in production, but it sort of shows you that it's perfectly fine to do many tasks. And for a small device, the kind of things you want to wait for are typically not, they can be sleeps, but it's often some activity on some GPIO pin, some hardware thing. You're saying, actually, I don't want to register an event listener that says, whenever you call this thing, give me an interrupt and call this function. It's much easier to say, okay, here, I'm going to set things up, and then I'm going to wait until something happens on this thing. And if you know that the system provides that functionality very, very cheaply, and you can reason out a system with tens or 20s of tasks that are sort of waiting, it's kind of a healthy alternative to sort of this using a single thread for many things. It's more like one task does one thing at a time. You get much better stack traces, you get much more sort of understandable code to this. At least in the context we've seen, it's been very, very successful. Are you guys familiar with like async and Node.js and operating system threads? And yeah. It's sort of it's been a topic over the last like 10 years or so. It's kind of nice. I mean, back in the day, people tried to solve this at the operating system level, and some people just sort of gave up and said, "No, we're just going to do like a library or Node.js and just do it at that level." And it is kind of clever, right? That you can get away with running so many things, right? I think we're much more in the Erlang camp in the sense that we try to build primitives into the system that gives you a way to run 100 or 1,000 separate things. In Erlang, it's usually processes. In our case, it's tasks and processes. I'm going to give you a super brief sneak peek into what we've put into the VM before just giving you like a short demo of what we've built here. But the sneak peek is simple. We made it really fast to call methods, which is like the one thing that a system like ours needs to do. So we call an append method on some list or array, pass a method. That needs to be really, really fast, and we found a way of optimizing that. And typically in these dynamically optimized systems, the optimizations require you to cache information associated with that call site. So remember what was the last method we ended up calling here. We found a way of doing it much more like vtables from C++ and Java, even without the typing. And we use a technique called selector-based row displacement to compress those tables. And then the result is that we have a way to run code on your device that doesn't require RAM to actually have really fast method calls. The kind of bytecodes that we typically end up sending to the device are super simple as well. Not a lot of typing going on in here, but a way of loading local variables, stack slots, loading small integers, the smi is a small integer, invoking methods like less than or minus and plus. And I think if you look closely at this, you will see that it's an implementation of the Fibonacci sequence. Given some input, it computes the Fibonacci sequence by checking if we're in some range and then subtracting 1 and 2 and adding the result. But the simple bytecodes are easy to make run fast on these devices. So at the core of it, the VM gives you a way to run code like this based on source code you provide, and it gives you that serviceability API that allows you to do these things for a device fleet. You want to see it? Let me see if I can show it. So I actually brought a device with me. The cable is not long enough, but it's here. It's an Esp32 Dev Kit, and then hopefully we can get some action going on in that. So let me just switch over. Go here, and I think the best way is just signing in. And here we have a couple of devices. One is running on cellular. It's actually back in the office, and the other one is running on Wi-Fi. It's the one I brought with me here. And this is sort of the console I was referring to, the dashboard for your devices, and I just put in two so you have something to look at. But at the core of it, you have a way of looking at the devices, how they're doing, what kind of data that they're sending. You can look at what kind of logs they're producing. Turns out it's connected to the Wi-Fi down here. And you have a way of actually running stuff on the device. And what happens when you do this is somewhat complicated, right? It actually takes source code from your browser tab here, compiles that, sends it in a form that can be sent to a device over Wi-Fi. My computer and the device is not connected, it's a separate power source. But it's really nice that it just spins up a new process over there, runs, in this case, a fairly boring program, Hello World. But it's kind of nice that you can do it, right? And it's very straightforward to just go ahead and play with this and say, let's say we want to run this 10 times instead, right? So it should be no surprise, but it just sort of kind of works in that way. So for experimentation, trying things out, it's great to have this kind of thing. I think in most cases, you probably want to use Visual Studio Code to do more of the coding, and then that's where you go to an experience that looks more like, I think, what you guys are used to, a way to type in code in an editor and run it on a device. And the way to run things here using the command line is quite simple. The device is called Wi-Fi, so I can go run Hello Toit, spell, on the device. And it's exactly the same functionality, built the same way, running on the device through that sort of scripting scriptability API there. You often find that it's kind of nice to be able to install things that don't run right now and instead sort of script when and how they're supposed to run. So what you can do is you can go and say, I actually want to define an application instead with an entry point and triggers. And you can say, actually, I don't want it to run just on boot. I want to run it on an interval every 10 seconds, and then go and deploy that. Oops, do that from here. How are we on time?
Good.
Perfect. In this case, we want to deploy the application definition instead. It says it's successful, that's a good thing, and we can go and take a look here at the device. It now has an application called Hello installed. It was created 9 seconds ago, and every 10 seconds it prints Hello World. Oh, I guess we'll see. Patience, it does. And once we're tired of that, we can just go on and install that and say, sorry, that was not interesting anymore. I think once we do put that in there, and we can say, let's go for like 60 seconds instead, 30 seconds, we can put this in the background, reinstall it. We can go and actually say that I actually don't necessarily want this device to be online all the time. I mean, it's okay if it goes to sleep if it has nothing to do. So we could tell it, say, I'm okay with you being offline for like a minute at a time, and we can say that. And then the device will actually now go to sleep, disconnect, but still have the application that we put on there in a form that can be run. And so with some patience and a minute of waiting time, we'll probably find that it goes back online and it runs the code and actually ran it even in the 30 seconds where it wasn't connected. So it just sort of services the kind of description that you put in front of it and allows you to write this high-level configurable code. It's always hard to demo things that requires patience. So I mean, I probably should have done like in the TV kitchen thing where you prepare everything as just a video, but it's kind of boring too. So let's see what happens in a few minutes. But at the core of it, right, you have this tooling, command line tooling, and the tooling built in here that allows the system to try to make your functionality run well on these devices. Let's see how it goes. Are there any questions or observations related to this? Oh, here we go. It actually reconnected after exiting deep sleep mode. And what you can see is actually that even before it was sleeping here, right, it reset after exiting deep sleep mode a couple of times and ran, I'll show you here, it ran the Hello World thing 58 seconds ago and ran again up here 30 seconds ago after a deep sleep mode was done. So just by telling it, I want this code to run every 30 seconds, the system says, okay, then in that case, I can only sleep for like 29, and then I need to reboot and start. And then I need to service the fact that you told me you want me to not be offline for more than 1 minute at a time. I'll do that separately and just make it all work out. So that's kind of a nice high-level thing. If you look at the configuration for a device like this, you can see that this is on Wi-Fi. If you go look at the cellular one, you'll find that this only connects every hour, and it's on TDC's narrowband IoT network, but that works really well as well. So at the core of it, right, you have here a way to write high-level code in a Python-like language, and you have the full orchestration engine that makes it really, really simple to deploy and deal with all these things. I just want to show you a final thing. If you care about that sort of Fibonacci example, it would look something like this, like less than 2. And here you see sort of the slightly different way we've decided to deal with parentheses. They're done for grouping, not for method calls. So in this case, to make sure that you have 2 separate calls going on, you need to add parentheses in a few places. There's no escaping that. But this is the way you would define that Fibonacci function that I showed you before. That's probably the shortest demo you can sort of do of a part of what we're trying to build, right? But at the core of it, remember that this is high-level code running on a dirt cheap little device with less than a megabyte of memory. It's dynamic in the sense you can install applications, they get written into Flash, go to sleep, it can run on pretty much no power, and you have this full system that probably wouldn't impress you if I if I ran all this in the cloud, but because it runs on the microcontroller, well, I'm not sure with you guys, but I think it's much more impressive because it runs on a microcontroller. And it's much more useful in settings where this kind of thing is a novel thing. So the reason why we're doing this is that there's just so much growth in this space, and the way people think of the future of IoT and the way they think of the future of computations at the edge of your network on devices is really based on the excitement around sort of graphs like this. This is from Ericsson, so clearly they have a vested interest in this happening, but I think they also have a good sense for what has happened in the past. Some of these are forecasted numbers, the Fs, but the rest is actually real growth. So for cellular networks, for this sort of massive IoT, like we are approaching billions of devices already. We actually have more than that. And all these things that are cellularly connected need a very lightweight way of getting code and data back and forth to them that can be scripted and changed 2 years after deployment. So in some ways, we need a platform like ours, or the platform that we've built here, to enable people to benefit from having all these cellularly connected devices out there. They're going to be there, but I mean, we get to make a choice if we want them to have outdated, kind of broken old firmware on them, or we want them to be computers that we can expect to be updated over time instead. I guess my money's on the latter with the software play that we're doing here, and that's the core of what we're trying to achieve. In some sense, it's also just sort of me, a software guy's attempt to try to make a part of the world that I found really hard to get into much more approachable for me. So it's sort of a self-serving thing as well. The way we've started on this idea of enabling all these cellular devices to be computers that can be used for interesting things today is that we've packaged up sort of that this whole platform, if you will, for your ESP32s. It's a starting point. We don't think that the ESP32 is the only thing that's interesting here. It's sort of a provocative choice in the sense that it's not something everyone knows of. It has great traction in the makerspace, and it's actually used in many more products than people expect. So we just found it sort of an interesting place. And the price-performance ratio is fantastic. Like, you get so much for so little. And with this, you can sort of deploy solutions on microcontrollers, like today, without having to give up on the kind of serviceability that at least I believe you need to be productive with this. And this is not just for me and my computer. We've actually shipped the first real version of the software that we spent like 3 years building, which is quite exciting for us. So people can actually go try it out for free and play with it, but just by signing in. And it does require you, at least to have the most fun with it, it does require you to go like buy a development kit like the one from PyCom and get the virtual machine on there before it really, well, you can augment that software on the device and make it a citizen in this environment. But once that's there, it's really, really straightforward to play with and build things on. We had at least a handful of students yesterday evening building weird things, and they had so many ideas on what they wanted to build with it. And it's kind of exciting to see that it's easy to get ideas here, and we think that we might be at least part of what could unlock making some of those ideas sort of happen in real life for real people. So if you have a project where like Raspberry Pi would be an interesting fit and something that could work out, but you think it's sort of overkill, maybe you should come to the Toit side of things. That's it for me. I think if you have questions, I'd be very happy. Maybe there's some online, or you said you had a microphone as well.
Let's give